Swayam Prabha. Digital India. Educated India.
So, the cover picture on this is a famous structure in Singapore. I think it's some 360 meters high with a cantilever of 6 meters, and it's called a skywalk. It's got a infinite swimming pool on top, infinity pool and all that. But it's supported on 3 vertical elements, and it reminds us of the story, the question I asked you about 3 persons holding a log of wood. We'll return to that in today's session. Okay. So this, in summary, was what we looked at in the introduction. What is structural analysis? We said it's all about finding the response of a given structure when it is subject to a given set of loads. And we looked at all the elements. What is a structure? How is it made up? It's got elements with certain properties. They are interconnected at joints. At the boundaries you have supports. We looked at all this. And it's subject to 2 kinds of loads, direct loads and indirect actions. And it responds. There's a force field and there's a displacement field. And normally the challenge is to fully understand the entire force field and the entire displacement field. There are some elements in the force field that belong to the loading, some elements belong to the response. Likewise with the displacement field. And we know enough about the structure. There are certain laws that govern the structure which make the solution unique, especially if it is a linear structure, linear elastic structure especially, which is what we're going to look at now. We also said that we have to make sure the structure is stable, and if the structure is indeterminate, then we have a choice of treating it as either statically indeterminate or kinematically indeterminate. We will look at that later. And then we said that we can do the analysis at different levels of refinement. Linear, static, deterministic analysis is the lowest level, which we should all know. But then there are some situations where the response is nonlinear. Mostly it is nonlinear. You get into non-linearity when you have what? When you have slightly large displacements. When the displacement response is large, it might move into material nonlinearity, and it could move into geometric nonlinearity. When we say behavior is nonlinear, let's say a load P gives a deflection delta or produces a bending moment M, then 2P should produce 2 delta and 2M, and minus 2P should produce minus 2 delta and minus 2M in the normal course of things. But that may not happen. And this is true of almost everything in life. If you go and buy, let's say, mangoes from the vegetable shop, 1 mango might cost you how much? Can you guess? You don't want to guess? How much will 1 mango cost? 30 rupees one. You must be eating expensive mangoes. Anyway, let's say 10 rupees. So, you're talking about 1 kilo, 1 kilogram. Or just 1 mango. Okay, 1 mango costs 10 rupees. 2 mangoes will cost naturally 20 rupees. 10 mangoes will cost 100 rupees. This is what we learn in school. But every housewife knows that, 100 is too much. You can buy it for, you tell me, 80. Some hard bargaining people will get it for 50. Right? And if you want to buy 100 mangoes, 1,000 mangoes, obviously you'll get a discount, right? The behavior of the salesman softens. That's called softening behavior. And the same thing happens with structures. They also behave like those salesmen. The response softens. So then you won't get the correct answer if you just do linear multiplication. But it works well and fairly accurately if the displacements are small, if the number of mangoes being sold are small. Then no bargaining. 2 mangoes, 20 rupees, no discount. Agree? The structures are also like that. No softening. Occasionally you will have hardening also. That's another topic. So the other advantage of linear behavior is, by the way, 0 mangoes should cost 0 rupees, right? So which means that that graph, the line in the graph between load and response must necessarily pass through the origin. Otherwise you can't play this game. But the other advantage is, in an actual structure you have different types of loads. And you have to do combinations of loads. So you have to do superposition. And you do it and you need to probably apply different load factors for different loads. You know that. So it's conveniently done by the software or even manually by having an Excel sheet where you apply a multiplier. And then if it's, say, 1.5 dead load plus 1.7 wind load, for example, then that particular column of load of reactions or bending moments or shear force, you scale by a factor of 1.5, scale by 1.7, then you add them all up under combined loading. That's called superposition. So all that is easily possible if you have a linear behavior. If it's non-linear, you can't just superpose, because both these loads act simultaneously. Each case has to be treated separately. So assuming linear behavior gives us a lot of convenience, and everybody assumes it, and the codes also allow that. Now, you have to be a little careful. Let's say you have, that's where static determinacy comes into play. Let's say you have, you're applying load factors, which means very high loads. And you might get into situations where you have material nonlinearity. For example, in a reinforced concrete beam, where the moments are close to the ultimate moment capacities, you might get some yielding, right? And so the structure itself changes. It's no longer the same structure that you analyzed before the loads were applied. And the structure keeps changing the more loads you apply. And finally it will collapse when it becomes a mechanism, right? So this also you need to know. It's called plastic analysis. But right now we won't do that. That's very interesting. Except in one class of structures where whatever you do, if a load P produces a moment M, a load 10P will produce a moment 10M. What are those type of structures? What are those type of structures where the force response is always directly proportional to the applied load? Yes? I'm not saying displacements. If the beam starts yielding, then the deflection will magnify suddenly and get large values. But the bending moment doesn't change, or the shear force doesn't change. In statically determinate structures, you can confidently do this linear scaling for the force response. Why? Simple question, simple answer. What is the meaning of statically determinate? Statics relates to forces. So the force response can be easily obtained by applying statics, the equations of static equilibrium. All you need is equilibrium. If you take a simply supported beam and you apply a load P in the middle, the bending moment at the midspan is PL by 4, even if the beam were to yield steel or concrete. Yes or no? Because the reaction will always be P by 2, and if at the midspan you multiply P by 2 by L by 4, you get PL by 8, even if the material yields. Yes or no? But if that beam were to be part of a multi-storied frame and you do the same thing, then it won't be whatever you get from linear analysis, because then some yielding will take place somewhere. Even the midspan it could happen, and then there's a redistribution, the game changes, because you're no longer analyzing the original structure, you're analyzing a different structure. And until it becomes a mechanism, it'll keep changing. Here, when it becomes a mechanism, when an actual plastic hinge forms in the middle of the beam, till that stage it will be PL by 8. And after that it can't take any more load, so it will fail at that load. So be careful when you go into ultimate loads, depending on whether the structure is statically determinate or not. You have to be. So linear analysis is always a special case of non-linear analysis. Similarly, static analysis is a special case of dynamic analysis, and I explained this in the last class. At least we should know how to do static analysis. Deterministic analysis is a special case of probabilistic analysis, but in reality most of the loads are probabilistic. Take for example wind load. How do you assess the wind load on a building? Normally you open a code, IS 875, and it gives you design basic wind speeds in different parts of the country, right? In Chennai, what is the design basic wind speed? 50 what? Meters per second. What does that mean? Basic wind speed is 50 meters per second. Then you convert the speed to pressure. Half rho V squared will give you the pressure. Rho is the density of air, and then you have to take the exposed area, and then you have to take the pressure coefficient, the drag coefficient, etc., etc. But it all starts with basic wind speed. What does that mean? How certain are we about the basic wind speed? What does it mean when you say the basic wind speed for a structure in Chennai is 50 meters per second? At least that we should know, then we can do. Because in the exam, you can get the loads and happily do it. But in real life, who will give you the loads? You got to figure it out yourself. And you have to make the structure safe. You have to make it code compliant. So you have to know, what does it mean? How will you assess that? What does it mean, 50 meters per second? Sorry? It is not an average data value.
Probability of 50 achieving the value is 50 years.
It's a peak wind speed. How do you get that? Let's say something happens. Right now there's some coronavirus spreading, no? So let's say it somehow comes here from China and everybody dies except you, right? And then you're such an important person, you'll be taken all over the world. You go to a country where you're the only person around, and you have to start from scratch. Let's say everything is destroyed, there are no more codes, books. How will you start assessing wind loads? You have to measure, right? How will you measure? You need some instrument. What's the instrument normally used? Anemometer. Where will you keep it? That's how at least you should know this. Where will you keep it? So the norm is you keep it in a place where it won't get disturbed easily. And will you keep it on the ground? Why? What's wrong? Ground is a nice place. Or someone might disturb it. No, you protect it. Huh? So he says the wind speed will be affected by the topography and the drag. That effect will be there even at a height. No, the simple answer is the wind speed at the ground is 0. Why is it 0?
Boundary layer.
Yeah, that's where the boundary layer starts. The wind speed has to be 0 because the ground is 0. Ground is not moving relative to the wind, right? So as you grow higher, the wind speed will increase. You have that drag. So that's called the atmospheric boundary layer up to a height called the gradient height. So you can measure anywhere provided you know how the wind speed is changing with height, and there are laws available. There's a power law and log law. Meteorologists know how to work it out. So we safely take a height of 10 meter. We've got 4 categories if you remember the code. Category 1, 2, 3, 4. So the reference category is category 2, which is open country terrain where you don't have large buildings or trees, and you keep measuring the wind speed on level ground. You have to make corrections for the slope and topography, and also for the roughness in the terrain. That's where all the 4 categories come, and you take measurements. How often do you take the measurement? Every day you take the measurement, okay? And then over 1 year, you should take the peak measurement, because you want to design for not the normal wind, which may be close to 0 meters per second, but for the extreme wind. Agreed? You pick that value, and let's say you do it over a long period. How long? As long as you can get. The more the better, because that's how probability works. You get large numbers. And over 1 year, you pick the maximum. That's called the annual maximum wind speed. The next year you take the maximum, and then all the maxima itself you can plot. You will get a distribution. It's called an extreme value distribution. What is it typically? Typically it follows a Gumbel distribution. They say type 3, whatever. And then will you take the absolute maximum of the whole lot? No, then it will be very costly to design any structure. You have to take some risk. How much risk will you take? Well, you take a risk of, you said 5%, because from how much risk will you take? Well, you have to go by what is called a return period. You heard the word return period? So a 50-year return period is typically taken. What does it mean? The basic wind speed of 50 meters per second, will it visit Chennai every 50 years? No, well, there are assumptions you make that, if you say the events are independent every year and it follows a Poisson process, and you say the probability of that basic wind speed being exceeded in any 1 year will be 1 in 50, which is 0.02, which is 2%. So 2% is a small risk. You said 5%, 2%. So everything is fine. You don't have to worry. It's reasonable. Yes? But you forget, this is in any 1 year. How long you want your building to stand? 50 years? Okay, after 50 years, somebody can demolish it. Okay, he decided 50 years. 50 years, if you want it to stand, then if the probability of exceedance in any given year is 2%, over 50 years, how much will it be? So you remember you studied some probability theory in school and all that. Once upon a time, well, you can work it out if you assume the events to be independent. It turns out to be 1 minus probability of not exceeding, that's 0.98 raised to 50. How much does that work out? 1 minus 0.98 raised to 50. Well, if you calculate, can you guess how much that number will be? 50%? 60%. Not bad, 64.5% roughly, which means there's a very good chance your building will be blown away. I mean, there's a good chance that 50 meters per second will be exceeded. It could be exceeded tomorrow, but definitely within 50 years, the chance is pretty high. So how do we take care of it in analysis? That's why we apply a load factor. And there are factors K1, K2, K3, you remember, risk factor and all that. So somebody has to do all that. But so having done that, we arrive at some number and we do the analysis. Please note, things are random. So be careful when you give results in structural analysis. You should know that first, your accuracy of your analysis itself is a big question mark. Secondly, the loads are very uncertain. Material properties are also uncertain. So when you report a bending moment of 498.3254 kilonewton meter, it might look good because of the accuracy, but that first digit itself could be off. Could be 5,000, could be 3,000. You understand? You must have a feel. Engineers must have a feel for probabilistic analysis. Okay? Everything you take with a pinch of salt. And statistics especially, be careful. According to statistics, if you put one foot in liquid nitrogen and the other foot in boiling water, on the average you are normal. So be careful. You should know that numbers are one thing, reality is another thing. Okay. So having understood this, we move on. Let me now tickle you with a simple problem, statics or dynamics. You've all seen this. This is called a common balance. We used to buy our vegetables in the market. What do? Typically, you select whatever you want. Your vegetables on one side, or if it's non-vegetarian, you can put that. And then you put weights on, the fellow puts weights, 1 kilogram, 2 kilogram weight, etc., 3, 4. And this thing will dance a little bit, and then when it becomes horizontal, you say, okay. Remember, even the kabaddi wala, you sell your old newspapers like that, he comes to your house. Remember, we did that. Nowadays also, we keep doing it. So let's model this now with a loading diagram, right? This is called a loading diagram. So I'm taking a fulcrum here, and this pan will apply a load here. This will apply a load here. Agreed? This is an idealized loading diagram. I'm catching hold of it in the middle. And the belief is the bar remains horizontal when the weights on both sides are exactly equal. And one way to check it is you give it a little tap, and there's a little dance it does about that, and then it goes back to. Yes or no? We totally believe in this. Now let's check out with our understanding. This is statically determinate or not? No, what is there? You hold, there's only one support, that too in the middle, right? Couldn't be easier than this. Now let's just check this out. Let's say I have WW and I put it in an inclination. Okay? Now does this, and so there'll be a reaction here 2W. Does this satisfy equilibrium? Sigma Fy equal to 0 is beautifully satisfied. And sigma m about any point equal to 0 is also satisfied. Now I'm going to argue that any position, any angle theta will also satisfy equilibrium. So why do you insist that the bar should be horizontal? Is that a good question? Anybody? I mean, this is...
But we are not looking about rotational equilibrium in that case.
Sorry? Any equilibrium. See, all the equilibrium equations you've learnt. Sigma fx equals 0, you apply. Sigma fy equals 0. Sigma m. Let me take sigma m about this point. Is that good enough? So W into, let's say this theta, L cos theta is equal to W into L cos theta, anti-clockwise clockwise. Does it satisfy? Then?
But the condition here becomes dynamics, not in the statics.
It is static. Why?
Rotation theta is,
Huh?
rotation theta is,
I am deliberately lowering like that, and I am releasing it. Well, how does it become dynamic? You want it to come to the horizontal state because you've been brainwashed into thinking it should go to horizontal. I am arguing there's no need. By applying equilibrium, there is no need for it to be horizontal.
It will be in a state where both the forces will be.
Array, you would give me an argument to show that I am saying theta can take any value. Theta equal to 0 is one value, but theta equal to 15 degrees is as good. It will work. Yes or no? Now you are wondering whether you were cheated while buying all those vegetables. See, when this goes down, does it gain potential energy or lose? It lose by, let's say, so much amount. But this other fellow gains by that much amount, so there's no change in potential energy. You're trying to use all the arguments you learnt in school. None of them work. So we came to learn structural analysis. I mean, basic, simple question. So there's a catch. Let me help you. You said dynamics. Actual behavior, if they were equal, is it will oscillate. Right? If you bring one down, because that is real equilibrium. How does it work? So maybe we made some error in the idealization. If so, what is it? Okay, this is a standard question I ask students, and normally they need to take one day to answer, and one bright guy next day in the class gives the answer. We don't have time, so I'll ask the question a different way. You have calendars in the wall in your room, right? So it is hung from a hook. Let's say you move it slightly to the right. What happens? It will dance a little bit like a pendulum and then come back here. Why does it do that? Huh? Why does it do it? CG, center of gravity is? Well, you're not saying it the way you should, so we will look at that. The bar need not remain horizontal to satisfy equilibrium, but that's because maybe this diagram itself was not correct. So this is where you have to have ingenuity in design. You must design the balance in such a way that it will work the way you want it to work. So how do you do that? Well, really it's suspended here on top, not at the center line. Right? And so there is a difference in elevation between, this is where the center of gravity acts vertically, right? There is a lateral shift between the point of suspension, which is always above the center of gravity. And that small shift is enough to give a restoring moment. Right? So it will swing it back. So you get a restoring moment because of this little eccentricity. That's a beauty in design. If you actually hold it at the center of the center line, it will, what I said, then it's called a compound bar pendulum, which is held in the center. Do you remember? So you have to be a good designer to design things that work, in which structural analysis can be applied, and you must also be very good in drawing your loading diagram. If you draw it wrong, you will get lost. Got it? Okay. That's just to tease you that you must idealize your structure correctly. So in engineering design, in such situations, the point of suspension is located above the center of gravity of the system, introduces eccentricity and thus a restoring moment. Okay. So this was what we looked at, and I think we covered it, and we all find it's pretty easy. Now we're going to cover all these topics. What can we assume in all these cases to quickly get the answer? These are all statically determinate problems we're going to first study. We'll also take a look at what statically indeterminate problems operate. For example, 3 people holding that log of wood. We'll take a look at it since we asked that question. But in statically determinate structures, what can you assume? What can you stop worrying about? What can you forget about? And actually, because we were trained to forget about it, our right brain stopped working. Displacements. So what can you assume the structures to be? Rigid. Agreed? Because all you need is statics. That's the first blunder we did while learning structural analysis, and engineering mechanics was taught like that. So, to find just the force response in statically determinate structures, it is sufficient to treat the structure as a rigid body and consider equilibrium or statics of the free bodies. First the overall free body, then you can cut a section everywhere, and every part of a body in equilibrium must also be in equilibrium, right? So you can find the internal forces. So you are never trained to visualize what the deflected shape is. So when you suddenly jump from determinate to indeterminate structure, the right brain is not yet, the left brain is very much active, logic, calculations, but right brain is weak, untrained, undeveloped. So I would suggest, as a good practice for a holistic understanding, it is desirable to visualize the deformed shape or the kinematics even for statically determinate structures, because that's the reality. Seeing is believing. You must visualize. And once you've mastered that, once enough neurons are firing from your left to right and right to left, it will help you in life, because you see everything in one big piece, right? And you can check. I'll give you examples of how this operates. So remember that example, 3 people holding. Can we use this as a loading diagram? Now, first, is there a catch in this like the common balance problem? No, this is pretty good. It actually can replace this with a line. The thickness is only, you don't need to worry, it's a line element. And this works with one big assumption. Remember 3 people holding a log of wood? What is that one big assumption? Very major assumption. That all 3 hands are at the same level, over level ground. Otherwise you have support settlement problem. So that's one assumption we make. Got it? So you've got one support here, another support here, another support here. And let's say you can put a roller here, roller there. So you have a horizontal force there, but sigma fx equals 0 says that there's actually no reaction there. So basically it boils down to 3 vertical forces. And then I asked you what's the answer, and remember, and you can see from symmetry that this reaction must be equal to this reaction. What equation are you assuming by saying this is equal to this? I mean, you use your intuition, but can you use your logic? Intuition, by the way, belongs to right brain. Yeah. You're saying if you take sigma mb, if you take moments of all forces about an axis that goes through point B, then you'll find that there's an anti-clock. VB is out of the picture, it has no moment. VA into L is clockwise, and VC into L is anti-clockwise, and this load W will, its CG will act at L by 2, so W into L by 2 will cancel anti-clockwise, clockwise WL by 2. So that's how you prove V is equal to VA. So you've eaten up, without your knowledge, one equation of equilibrium. So we've eaten up 2 equations of equilibrium. What are they? Sigma fx equals 0, that's how we proved this is 0. And we proved mb is equal to 0, sigma mb equals 0. If you say mb equal to 0, you're saying the bending moment at b is 0. We are not saying that. Sigma mb equals 0. Then we proved this. We got one more equation. What is that? That this plus this will add up to w. Agreed? That's it. That's all that we have. Now, we've got 2 unknowns because this is equal to this, and we have 1 equation. Can we get some more equation by playing some games? No, we are doing equilibrium now. You can say sigma ma equal to 0. Will we get a fresh equation? Yes or no? You will get a new equation. But the problem with that equation is what? So a bit of maths you should know. So why? We can get hundreds of more equations. You can take sigma mc equal to 0. You can take sigma y inside the b. You can take a point here, and about that point is 0. Point here, point. How many points are there? Infinite points. So I can write infinite equations But I'm just wasting my time. Why? They are all what? So at least you should know this. You must correctly say it. So finally you have to solve simultaneous equations, linear simultaneous equations. So basically you can write it in matrix form. You have a coefficient matrix and you have unknown, in this case forces, and this when multiplied you get some constant. So this is constant, that is right. Let me give an example. Let's take this example. We'll say that x1, this is the middle support, okay, x1 plus 2x2, this is a reaction on the left and right, this is equal to w. That's one equation. That's all we have. Now, why not write another equation? 2x1 plus 4x2 equal to 2w. Lovely equation, no? Then an even better one. 3x1 plus 6x2 equal to 3w. I simply added these two and wrote this. So I can write 1000 equations. 1000, I'm using IIT lingo, so you'll understand. But basically you'll find that they are all linearly dependent and they'll reduce to just one equation. You're just wasting your time. And how can you make out from the matrix A, this is called the coefficient matrix, by looking at the rank of the matrix. Remember, once upon a time we studied something, rank of a matrix. If the matrix size is say 3 by 3, unless you get a rank also 3, rank is the number of linearly independent columns or rows. And there are ways to check it. I've covered this in my NPTEL course in Advanced Structural Analysis, the book also. So mathematics, linear algebra is lovely. You can get the hang of it. So we have a situation where we have more unknowns than available equations of equilibrium. That is a problem in statically indeterminate. So we can't look at statics to crack the problem. We have to look in kinematics, in which we have hardly had any training. Right? So let's go slowly because soon we'll get into kinematics, and let's see what's happening. So remember the first guess those people gave, they are not present today. W by 3, W by 3, W by 3. They said off the cuff, 3 people sharing the load, okay, W by 3. No problem. Then some smart guy realized, no, the middle fellow is sweating it out. He must be supporting more. So he said W by 2, W by 4, W. Remember, do we agree intuitively this is the correct answer? Now logically this is correct if we can draw some free bodies. For example, if you draw a free body like this, we cut the beam into 2, then it makes sense because you get a reaction here, W by 4, W by 4. And when you add up these two, this is what the middle fellow is going to take. So that makes sense, W by 2. So is this correct? Is this correct? Will the middle fellow be taking W by 2 or more than W by 2? More than W by 2. Why more than W by 2? Why? See, W by 2 is a major improvement over W by 3. Now you are saying even W by 2 is wrong, it is more than W by 2. What is your argument basis?
Continuity will be lost.
Yeah, so you are saying when you cut this beam, you lost the continuity. If you get back the continuity, what is the extra force that comes into play? There will be a moment. You know that at a continuous support, there will be a hogging moment, right? You're right. So then you know that actually there is something more to this, and that is there is a moment. See how I guessed your guess. M is there. Hogging. So it will act like this. This M, what does it do to this reaction? This has to be self-equilibrating, right? So you will get reactions like this. If you divide M by L, you get this reaction. This forms a couple. Now this is in equilibrium, this is also in equilibrium. Got it? So what's happening is, even this is wrong because on top of this you're going to get 2M by L. And this is going to be reducing by M by L because it's acting downward. Right? All this beautifully we understood just by statics and this intuition that there's going to be a hogging moment there. Got it? Very good. The WB is definitely greater than W2's. Now the question is, we can crack this problem only if you know M. How the hell do you get M? Huh? How do you get M? Don't complicate things here. What unit rotation? How will you get M? Simply take that M and shove some value. Can I give M any value? So what you ended up doing is, when you say, if I know M, I got all the answers. By identifying MB as a redundant, we are treating the beam as being internally statically indeterminate. So I want to bring that concept. Normally we would have thought this beam is externally indeterminate, right? Unnecessarily one extra reaction. That fellow need not have come in the middle and support it. We were happily knowing W by 2, W by 2. He came and created this problem for us. He made the whole problem indeterminate, unnecessarily coming the way. Redundant fellow, if he had been out of the picture, everything would have been fine. Yes or no? Correct. Now, so that is, he is a redundant reaction. So you are treating that as an external redundancy. But in this approach, you only told me there's a moment there. You can take any redundant, by the way. This is more interesting. Here, you have to cut the section to expose this moment. So it's an internal. You could have taken any redundant. You could have taken the shear force here, whatever. So this is more tricky, but you should know that if you're great in structural analysis, you can take any redundant. Only one, because the degree of static redundancy is only 1. Okay, so far so good. Now you have to visualize the kinematics to crack the problem, ideally. We'll do that later. Now infinite solutions are possible. So let's look at some solutions. This is one solution, but we know that this is wrong because this has to be more. Okay, let's take another solution. If you take this solution, then this is a bending moment diagram, right? Because they're basically two separate beams. What is the moment in the middle? It will be W by 2 into L by 8. Or if you take the reaction, it will work out to WL by 16. Normal beam, WL by 8 kilonewton meter, if W is in kilonewton. But if it's half the load, W by 2 is the load, W by 2 into L by 8, WL by 16. Got it? Sagging moment. We all know this. So bending moment diagram is known. Now let's just guess. We don't know. We don't know how to solve the problem. In the olden days, they used to just do that. Okay, let's guess. Let's say it's WL by 16, the same. Then if you plug in this value, you'll get this reaction, this reaction, this reaction. And if you draw the net bending moment diagram, you'll get this moment. If this is positive, I'm drawing this negative. And your net bending moment diagram will look like that. Remember, hogging in this region. See, remember, point of contraflexion, this part is hogging, this part is sagging. Fine. This is one solution, but we don't know if it's right. Then somebody says, why are you taking WL by 16? I'll take WL by 8. You just substitute WL by 8, then this diagram will change to that. Third fellow says, why WL by 8? Let me take WL by 4. If you take WL by 4, very interesting, then this reaction becomes 0, this becomes 0. It's like those two fellows are relieved of the load and they are happily relaxing, and the poor fellow in the middle is taking all the load. That is also possible, right? But you will get a completely different bending moment diagram. It will look like this. Or like that, you can keep playing the game WL by 2 and any value in between, then it will look like that. Now, which one is correct? Multiple choice. Now there are 100 people in this room, I can get 100 different answers, right? And for each answer, you can get a bending moment diagram. Why? You cut a section anyway, once you guess this value, you can find the bending moment anywhere. Agreed? Yes or no? So how to check who's closest to the truth? I've got 100, actually I can get infinite solutions. The same one individual itself can give me 100 solutions. But we have 100 people giving one solution each. Let's say you're not copying and you're all doing it originally, all different answers. And for each case, can I ask you to calculate one quantity, and then by comparing that quantity, I'll decide who is closest to the truth. Strain energy, see, not bad, right? So we'll see how that happens. Good. So which one is correct? By the way, I could have reduced the complexity of this and made it into okay, this is BC. This part I take, and I could have made this into a prop cantilever and analyze this, and I'll get the same M. Is it true? Clever engineers do that. Big structures, why make it complicated? There is an axis of symmetry here. Mirror image, left side, right side. I can either work with the left or with the right, it doesn't matter. Now I must put the correct boundary conditions, right? Here the deflection is 0 and the slope is 0. So I'll get that when I make it fixed. So instead of, now this looks like a less complicated problem, but this is clearly statically indeterminate, right? I could have done this, and if you know, say, conjugate beam method or some method like that, you could have cracked the answer. The deflected shape will look exactly like this, and probably you'll get the answer. The answer happens to be this answer, by the way, the first one. But that's another clever way of doing it. So a little bit of understanding. So for that, you would have done this only if you saw this diagram. Now, why is the slope there 0? Can you give me a logical answer? Why is the slope there 0?
Pass from.
Why is the slope there 0? Give me a logical answer. I am a left brain guy. I know intuitively for symmetry it looks nice like that, but logically tell me. You have to give me a compatibility argument. So what's the correct way to do it? You should learn logic, then you'll know. So you'll say, okay, let it not be 0. You're happy. Let it not be 0. So let the slope there be theta. Now you choose. Do you want theta to be clockwise or anti-clockwise? I like clockwise. Okay, clockwise theta. If you give clockwise theta, that means the slope is going to be like that. You have to agree for compatibility, because you have not cut the beam. The theta here and the theta there must be the same. Then obviously you lost the mirror image. Okay, make it anti-clockwise. Then also, so there's only one solution possible. So even the hard logician will say, okay, given it's 0. That's how you do it. You must be very strong in all this. Total clarity. Left brain, right brain, any way you can look at it. Ideally both ways. So this is the correct answer. You see, this answer will give you this, which you could have got from this. Now let's see how to get this answer. You said that you learned somewhere that where the total stored energy is minimum, right? So let's say I ask you to calculate the strain energy, okay? All of you. Actually you're calculating, you're using this formula, remember? There is a half, that's why the bottom, we'll come to this in part 3 in this course, but I'm just giving you a glimpse. You remember? So you got the bending moment diagram. Remember, we've got infinite diagrams. You got all the diagram. I ask you to calculate. You can calculate whichever way you want, and you will come with a number. Complementary strain energy, it's called U star, and the units of it will be What is the unit of energy? Joule, okay? Joule. So nothing wrong. So you'll get in joules. How many joules you got? Say 20 joules. He got 15 joules. So I'll say, who got the lowest joules, provided you did your calculation correct? Say, most likely you got the right answer. So when you plot, you get like this. Strain energy is always positive. You could even give me ridiculous answers like bending moment is sagging, not hogging. And the correct answer will come here. But you need not do all this. We are all IIT students, so we say, sir, we don't do all that. We do simple calculus. We'll take the derivative of this and put it equal to 0, and then we know the bending moment. We can crack this, and you will get this answer. All of you will get the answer, not one person. So there's one way to do it. We'll see it later. It's called the theorem of least work. Actually, you have to do less work to get it. Why? Because nature is always economical. It will always conserve energy. It won't waste energy. It will put the minimum strain into the body. But the more popular method is method of consistent deformations. Might as well go through it since we touched the topic. So let's say now we'll treat it as externally indeterminate. And we have these equations, right? Two equations, VA is equal to VC and VA plus VB plus VC equal to W. And we've got three unknowns and two equations. And so by identifying VB as the redundant X, we are treating the beam as being statically indeterminate. The moment you identify the redundant, you are identifying what is called the primary structure. Here the primary structure is the structure without this redundant. So basically you remove that support and you back to this support, the two people holding at the two ends. And this is statically determinate. That's called a primary structure, a single simply supported beam. On the same primary structure, you apply both the loads and the load separately, and you should know how to calculate deflections. That we'll see later. Now you know the formula and all that, but there's a way to calculate deflections, and you have to push back the beam such that this deflection is completely neutralized. And you know the formulas for a simply supported beam with a constrained load and with a UDL. You equate these two together. That's your third equation, the compatibility equation. And then you can solve this and you get this answer. And then you can draw the bending moment diagram. Got it? We all know this, so at least we should have known this. Now, remember the internal indeterminacy method. We should also look at that. Supposing we made M the redundant, then your primary structure is two separate beams, and this is the loading and this is the redundant. Here, what is the compatibility condition you are going to apply? Theta. So you got the bending moment diagrams for both, and now you're saying this is going to deflect like this is going to deflect like this, and this rotation here is neutralized by this rotation. And you must know how to calculate these rotations. And let's say you know the formulas, and then you get the same answer. Are you getting it? But the moral of the story is this: get a feel, visualize the structure. Is it going to deflect downwards, or is it going to deflect upwards? Is it going to rotate clockwise, anti-clockwise? Are you making it compatible? Are you going to get hogging moments or sagging moments? All that you need to know. So, for example, finally you get this answer. You should, when you draw it also, this point should be located exactly where it's going to switch. So, that small round I've shown there is, you might as well put an internal hinge there, because that's a point of contraflexion. Are you getting it? A good engineer will draw nicely, not just something, and it will match, this diagram will match with this diagram. And you've drawn it on the tension side. So you know you need top steel in this region, you need bottom steel in this region, in a reinforced concrete beam. Are you getting it? And that's skill. You can make out who is a good engineer, who is not, because it will be roughly to scale. In this case, this value and this value are equal, so it's not drawn exactly perfectly. Okay, good. Next topic is, we often see drawings like this. Even question papers I've seen written like this. Bad question. Why? This is a bad question. Why is it a bad question? Because you're all, some of you are going to become teachers, no? You will set questions like this. Bad. Why is this a bad question? So now we are all trained. We were taught badly, so we know that these are reactions we know. Right? But nobody says anything. So I want you to know about good questions and bad questions. Let's say you want to teach about barometers. What do barometers do? Measure pressure. So let's say you ask a question. How will you measure the height of a tall building using a barometer? Good question. Now you can get many answers. You have a bright student here who says, "Sir, I will tie the barometer to a rope and lower it to the ground and measure the length of the rope." Is it wrong or not? Other fellow says, "I'll just drop it and measure the time it takes to hit, and I know by equations I can solve it." Third fellow says, "I'll hold it on the top, measure the shadow on the ground, and I know the azimuth of the sun, and I can." All of them are correct, but you will mark them wrong because that's not the answer you have in mind. If you want the answer you have in mind, you should write the question correctly. Using the principle of the barometer, how will you measure the height of a tall building? Similarly here, I don't know what you have in mind, but then you should realize what you drew is a free body diagram. Just showing arrows without supports is a free body diagram. What is the meaning of free body? You're freeing the body from supports. You are freeing the right brain completely. Right brain, go to sleep. Only left brain need to work. Only statics. Right? Very dangerous. That is how we've been taught, that's how we teach. Don't do that. You should know the difference between a free body diagram. This is what you had in mind. But we often draw this, am I right? Now, the problem with this is, we'll go back to the barometer story. I could give an answer that this reaction is 24 and this is 0, 0. You can't mark me wrong. Yes or no? So, for example, I'm assuming, so this is the correct answer. I'm assuming, or I could take this, the 24 is shared here, 12, 12. So I'm assuming a support which is very flexible. Or I can assume a support which is restrained here, but here very flexible. So all these answers are correct. Infinite answers are possible. So I want you to understand the importance of drawing correctly a loading diagram before you start your analysis. Yes or no? Let's take just one more topic before we move on. Take this problem and let's put a load on one side of the beam. Okay. Now this is a loading diagram. You clearly showed that no deflection possible here, no deflection possible here, no deflection possible here. Rotation should be equal on the left and right. And load is applied here. So if you try to analyze this, you write your equations. I won't waste time. You can do this. And again, I can give multiple solutions. I can give this solution. All are statically admissible. Right? Now, you can apply compatibility and solve this. but I want you to also understand each solution you give has an associated kinematics to it. For example, if you're giving a solution like this, what is the probable deflected shape you have in mind? Okay? Yes, you are assuming this. Where this part won't even bend. It will go as straight because the bending moment there is zero. So when you gave the solution which is statically admissible, kinematics is not admissible because it is going to lift off. You can imagine the others, but I'll draw the last one. This is the correct solution. For that, it has to come back here. Are you getting it? So please note, every force response has with it an associated kinematic response, whether you know it or not, whether you like it or not. And a good engineer knows what bungle you've made, because your right brain has gone to sleep. Okay. So the correct solution must also be kinematically admissible. Now there are a lot of geotechnical students here, right? So here I'll tell you a common mistake made in practice. Nowadays, people use softwares like SAFE and they don't know what's going on, they just design. But in the olden days, no softwares are there. Let's say you have a 3-column footing. How many of you are geotechnical? MTech? Suddenly nobody is in geotechnical. Okay, quietly you're raising hands. Whether geotechnical or structures or transportation, the question is the same. So you need to design this. 2-column footings, single isolated footing is very easy, supposedly. But sometimes 2-column footing, the footings are clashing with one another, that's also easy. Why? We'll see later. 3-column footings, be very careful. So let's say this is a 3-column footing. This is cross section will look like that. Okay, I put a beam and a footing slab, and I'm making the assumption that it is rigid. We normally make that assumption, no? Rigid foundation. What's the advantage of making the rigid foundation? Huh? Geotech people tell me. The structures people tell me. Settlement. Okay, so what does that mean? What does uniform settlement mean? Geotech straight goes to settlement. Structures people don't want it to settle at all. What does it mean? Contact is always there, but more important to analyze. The pressure is always going to be linear. If it's symmetric, it will always be uniform. This is symmetric. Agreed? Actually, it won't be uniform, but for ease in analysis, we make. Yes or no? Whether that is right or not is a different topic, but having made that assumption, agreed, take the total load. Total load is 3P. The contact area is B into 2L. So, total load divided by total contact area, and if you treat it as a beam, then this B you can remove. This you will get an answer in kilonewton per meter, like a beam with the load applied from below upward. Yes or no? Now the moment people see this, they say, oh, this is a tricky, this looks familiar when we put it upside down. Yes or no? Then why not do it same thing upside down? First you do one upside down, then you do another upside down, and this is how many people design it. Yes or no? I've talked in Larsen and Toubro, they also used to do this. Okay. Anything wrong with this? Anything wrong with this? Well, let's check it out, okay? We should not dismiss. After so many people have been doing it, there must be something right in it. Now we are good in doing, we already mastered that. 2-span continuous beam, we know the answer. Alright. So, you do it ulta and you analyze this there's only one problem. You will end up with reactions which are not matching with the loads that you got on the columns. Original load were PPP. But conveniently you close one eye and say everybody is doing it, so let's some approximation. Alright? And then you analyze this beam and you got the shear force diagram, you got the bending moment. Remember 3 PL by 16 P is, you will get something. Okay? For this, you will get this loading because the loading is this. You will get this answer. Total load is 3P. So remember WL by 16 we got there, we got 3PL by 16. Then you will get something here, fine. And people have designed and these things have been built and they are standing. Alright, very good. But only one problem you have, my God, this actually is not matching with the PPP, which was the actual load coming on the column from the loads above. Okay, now the challenge is, actual loads were PPP and you got these as your reactions from this analysis. But now let's take another horrible condition. Let's say this is heavily loaded for some reason. This is very lightly loaded for some reason. Load is almost zero. Maybe it's a freestanding column, no slab, whereas this has got heavy loading. Possible or not? So if the loading is 0 3pp, 3p0, this analysis will not change. So you are going to give the same design of the footing, not giving a damn to what the loading is, provided the total load is 3p. That somewhere you know something is wrong. But so many people are doing it, can't be wrong. You know the story of the emperor's new clothes. Someday I'll tell you, we don't have time. So, okay. Now, what is the mistake? Obviously it can't be something, you can't give the same bending moment diagram for this loading and this loading. Surely not. Rigid foundation design has been widely accepted worldwide. Now don't say actually.
Load is not uniformly distributed.
The same thing he's saying. I'm assuming rigid foundation design. It is uniformly distributed. You are giving the wrong answer. You are answering some other question.
My known values are the reactions, not the...
Yeah, that's what I'm telling you. For this, you should have got a different bending moment diagram for this bending moment diagram, but you're giving me the same bending moment diagram regardless of these loads. You are giving me reactions when I'm giving you loads. What is this? I gave you something, 100 rupees, you are giving me back 50 rupees and saying everything is fine because everybody is doing like this. I demand my 100 rupees back. Another fellow is giving you 1000 rupees, you are still giving him 50 rupees. So what's the mistake? First let us clear the cobwebs here before we do any analysis. What's the fundamental mistake? Anyone? What? So how to make the correction, you tell me.
In actual foundation level, their deformation will be different than this edge.
Oh, definitely, but our right brain stopped working long time back.
So we know the reactions. Now we have to find a bending moment shift second to those reactions.
What to do? You tell me. You are giving me all explanation. Tell me what to do. Sir, what to do?
You have to find the Q not using the static.
Oh, complicated. Simple answer. Who the hell asked you to analyze it as a statically indeterminate beam? Huh? Sorry? You want to change the support conditions. You can make anything. Oh, you're saying you will want to make this a roller. It won't change the answer. Answer will still be the same. Oh, you're not see. You are blind. I don't like this. You see the original problem. Obviously wrong. See the correct solution. Look at the problem. This was the problem. You made the rigid foundation assumption. Why the hell did you convert into a two-span continuous beam? Ulta. P, you got this. Everything is known. Can I cut a section here and get the bending moment? Straightforward. I've given you a cake to eat. Cut also. Please eat. You want to bake a fresh cake. What the hell are you doing here? You understand? The obvious itself we mistake because we have learned so much. Better unlearn all that you learned. So, you'll find that this is, you can cut a section here, you can draw the shape of, this is the bending moment diagram. And if you take the other load case, you'll get this bending moment. This and this are poles apart. That's all you do. The rigid foundation is an assumption, but having made the assumption, which is acceptable, you should know what to do. Don't unnecessarily make determinate structures into indeterminate. First, you made the mistake of making an indeterminate structure determinate and you said WWW or you said whatever. Now you're doing the opposite. I gave you a determinate structure and you made the damn thing indeterminate because everybody else is doing it and it looks familiar. Only thing it was upside down. Madness. So, is it a good introduction to structural analysis? Don't be mad. But you're right. I want to do it more accurately. Then don't make the rigid foundation assumption. Put it on springs. Winkler supports or Timoshenko beam or whatever you want. And then if you analyze it properly, you will, rigid foundation means all the springs are infinitely stiff. And we'll get the subgrade modulus and do it correctly. And then you'll find that the actual deformation will be like that. And then you can analyze this, but you need to get this correct. But there's uncertainty in this also. So be careful. So you must get bounds, lower bound, upper bound, and do it. Okay, so we'll stop there because it's 6:15 and we have to close shop. Thank you. We'll continue tomorrow.